Hi, everyone. I'm Dan Powers. I'm the Executive Director of the Society for Science and User Research Facilities. This is another session of our 2021 annual meeting. We're going to feature a spotlight on exascale computing. We'll learn from Dr. Douglas Koth. He's the director of the Exascale Computing Project at Oak Ridge National Laboratory. And the Exascale Computing Project, the ECP, will provide the capability to tackle challenges in scientific discovery and national security at levels of complexity and performance that previously were out of reach. I think with that very understated framing, actually, let me turn this to Doug to describe the awesome topic and impact of the ECP. Doug, to you.
Thanks, Dan, for having me. I will share some slides here. Let's see. Is that the right view, Dan, and everyone else?
Yep, that looks right.
Okay, well, I'm going to take it away. Again, thanks to Dan and SSURF for having me here. Full disclosure, I was not familiar with this organization. I probably should be. Thanks, Dan, for reaching out. Really excited to establish connections and hopefully lead to longer term collaborations. We do have a lot of lessons to learn. Lessons learned to share and probably still to learn as well in ECP, as we call it. And looking at the member facilities, we have direct ties to a number of member facilities in this project. And I'm pretty confident in direct ties to most other. So I'm going to focus a little bit today on not just the project, but where I see ties with other facilities where we're collaborating and trying to help them enable science or better science. I want to thank our Department of Energy sponsors, Barb, Helen, and Took Hong, and the Office of Science and NNSA. These same sponsors do support, I think, some of your member facilities. Our mission need in the project really does require delivery to a number of program offices across the Department of Energy and the Office of Science, Applied Energy, and Defense Programs. So in looking at your member facilities, we hit a lot of these facilities, so to speak, with regard to our overall mission need. So a little bit about ECP. It's a project that's been going on since 2016. It's a part of a broader exascale computing initiative, which I'll in the next slide show what the scope entails. But again, as Dan noted, we want to accelerate innovation with exascale simulation and data science solutions and enhance U.S. economic competitiveness, improve our quality of life, and strengthen our national security. It's a very broad statement. Hopefully I can convince you that ECP is doing its part on delivering applications, creating a software stack that supports those applications, and leveraging United States high-performance computing vendor R&D. We really are quite confident that we're 5 years into this project. We're on, I think, a really good trajectory to deliver on our mission and realize our vision. Again, ECP is part of what's called the ECI. This was a formally funded initiative in the Department of Energy in 2016. It consists of three parts. This project, procurement of the first three exascale systems at Argonne, Oak Ridge, and Lawrence Livermore with Aurora, Frontier, and El Capitan, and selected Office of Science Program Office investments as well. So this pie chart is not to scale, but nevertheless, ECP is a large, very exciting project. I'm really happy to share where our status and where we're going. Again, it's I mentioned 7 years. It's a large project, 1.8 billion over that time frame. There are 17 Department of Energy labs, and 15 of those 17 labs participate in ECP, with 6 labs lead the effort. These 6 labs listed traditionally been heavily involved in high performance computing development, applications, and system procurements. So not surprisingly, these 6 labs were asked to help lead this endeavor. I'll say a little bit about our focus areas, as we call them, our scope and what we're trying to do and our anticipated outcomes. Overall consists of about 1,000 researchers in groups of 80 plus R&D teams, and not just DOE lab scientists, but scientists from US industry and from academia. So it is a large project with lots of moving parts. I'm going to leave these slides behind. This is wordy, but a little bit of retrospective, which is DOE has been involved in HPC, since the 1940s. So we have a lot of lessons learned here to share. It's been a mainstay of the Department of Energy, and really mod sim and computational and data science has never been more vibrant and foundational. than it is today. Accelerated compute performance isn't just getting answers faster, but it allows us to get higher fidelity solutions, higher confidence solutions. So think of lower error bars, lower margins, being able to develop designs in a much more, say, short-term way and lower cost. The exascale era, as we call it, and I think it's here, is upon us, and we're ready in the ECP to show what we can do on these systems that are coming. So again, really happy to be able to share a little bit more about this project and what we've been up to. ECP's focus areas really consist of 3 technical areas: application development, and you see we are supporting 24 applications and several co-design centers that I'll mention here momentarily. An entire integrated software stack that consists of 71 separate products, and this stack sits on top of the vendor operating system, but underneath the applications use these components to be able to do their science, and I'll say a little bit more about that as well. And then we funded some US HPC vendor R&D to make sure that these systems delivered have node and architecture designs that meet our simulation and data science requirements. I don't really usually show org charts, but I really wanted to point out a couple things. Our program management, we're funded by 2 Department of Energy programs led by Barb, Helen, and Tuk Hong. John Young is our federal project director. You'll see people from all 6 labs asked to lead the effort here. I would like to call out Lori Dyson at Lawrence Livermore, my deputy director. And we have really key leaders in the field who have been senior people that have stepped up and agreed to lead these efforts. Also really want to point out that from the start, we've embedded and structured ourselves to where we reach out to industry, U.S. industry, and selected government agencies. Industry and Agency Council there, led by Dave Kepchinski at GE and Fran Hill at the DOE HPC mod program. It's a really key aspect of our outreach. The council members are shown here in terms of their company and agency logos. We have 5 government agencies and order 15 or so industry members, and they engage with us monthly and quarterly and longer meetings every 6 months, where we share what we're up to and they give us feedback on is what we're doing useful for them, and if not, what makes the technologies more useful. So really, we're interested in making sure that the technologies we developed are pushed out and exported into the U.S. economy. So the roadmap to exascale systems are really here now. Frontier is being delivered at Oak Ridge as we speak. Aurora will be coming shortly thereafter, and El Capitan shown on the right here. What's interesting is relative to a little over 10 years ago, where GPUs were kind of new and novel, NVIDIA graphics processor units, now they're ubiquitous. And not only do we have NVIDIA accelerators that we've really learned how to program for our science and engineering good, but we have AMD and Intel's GPUs that are here or coming. So a rich ecosystem of accelerators, as we call them. And accelerators, in my definition, is hardware that's designed to specifically accelerate floating point operations. So here you see diverse ecosystem. This is very good, but also challenging to make sure that we are portable to these systems with our applications, but also can perform at the level expected. The specs for these systems are daunting. They're just super impressive. I'll encourage you to go online. Slides that give links here for how in the Oak Ridge Leadership Computing Facility, which is an SSURF member facility, as well as ALCF and NERSC, see how things have evolved, sort of current state, which was order circa 2016, and evolved to now. A couple of themes here. You have nodes now that are 50 or hundreds of teraflops, so big, fat, compute, powerful nodes, and the 5,000 to 10,000 nodes, not 20, 30,000 nodes as in the past. So we're really sort of scaling in instead of scaling out, which has its strengths and weaknesses and benefits and challenges, but we're excited these systems are here or coming. What are we supporting in application space? This is really lines of sight to key pillars of strategic importance in the Department of Energy: national security, energy security, economic security, scientific discovery, Earth system, and healthcare. And all these applications were carefully selected in consultation and guidance with our DOE program offices or stakeholder offices that really align with these applications, and the problems they're trying to solve are of strategic importance. So the starting point in 2016 was a lot of code, a lot of what I would call legacy code, millions of lines of code, and ECP, we're surgically targeting certain pieces to redesign the software, the architecture, to enhance the algorithms, enhance the physical models, put in new physical models. So each application has its own unique development plan, targeting a specific challenge problem with very specific kind of diverse, institutionally and disciplinary diverse team. So in terms of what we're doing, it's demonstrating that we can address challenge problems. These are problems of strategic importance to the Department of Energy stakeholder offices, problems that are minimal to mod sim and data science, and problems whose solutions really will change the game. So a lot of what we're doing is developing the applications, demonstrating that we can do the challenge problems, address them. So we're, that includes targeting new science opportunities, doing lots of demonstrations, and then the handoff post ECP is to do production science and engineering, to really use them as science and engineering instruments for decades to come. And so we've been working very hard. I'm very confident that we're going to realize this vision. So, it's not just porting. Porting's hard enough, but we have to adapt the numerics and adapt the physics models with regard to making sure these applications run well and run better with more enhanced physics on these GPUs. So there's a lot of moving parts. It's not just a port. It's a lot of really roll up your sleeves and hardcore algorithm development and software development. And we're fortunate to have great teams to be able to do this kind of work. And this is just give an example. We've been working with the teams to give them multiple choices to port and have the applications perform well on these incoming systems. So they can take approaches where the programmers have less control and there's higher level abstractions. So there the portability is sort of higher. But if they want to get really down into the metal and get into the weeds and have more programmer control and programming more native models, the portability may not be as enhanced, but you'll get great performance. So the applications really kind of weigh the pros and cons, and you can see they have multiple paths to do this that we've supported in ECP, and it's really represented in our software stack. So where we've gone from 2012 here at Oak Ridge National Lab with the Jaguar system and the Titan system is from, single CPUs or multi-core CPUs to one GPU to now to multiple GPUs to a diverse set of GPU environments. I mentioned 3 types. And now we're really moving to GPU resident, where the entire application really does move down on the GPU and lives there the entire simulation. It's where all the action is. It's where the compute horsepower is. It's where all the memory bandwidth is. On Summit, for example, out of the 200 petaflops on the Summit system, only about 5 or 6 petaflops are embodied in the CPUs. So unless you go use the GPUs, you're really looking at using a system that's 10, 15 years old. So GPU resident is the name of the game. And it's not easy, but our teams have really been moving forward and generating impressive results on the Summit system. Here you see, and apologies for the acronyms, a collection of ECP applications. And the figure of merit is basically performance ratios of current performance on Summit relative to their performance in 2016 on, say, the Titan system. So, the goal is, hey, let's shoot for at least 50x. And you can see that of this list of applications, all but a couple have already achieved that. Some greatly surpassed our expectations in sort of revisiting and rethinking algorithms. In particular, the algorithmic strides made outstrip the hardware strides. And instead of getting 50, they're getting 100, 200. And, it's not just saying you're going to run faster, but you can do tremendously better and more productive science. It's really a game changer in many cases. I'm going to take you through a few examples that really point to, in fact, other facilities. So here is a very non-traditional HPC application, really has a line of sight to the BER office and the Office of Science, and the key facility that it's targeting as a production assembler is JGI. So this is doing metagenomic analysis led by Kathy Yellick, a fantastic project where you're going to compute the genome sequences on communities with thousands of microbial species. And that's really useful in environmental, plant, animal, and human health. So the challenge problem is demonstrating that the assembler can process 50 terabytes of environmental data. This algorithm genome sequences is not at all well suited for GPUs. It's taking a bunch of small genome reads and trying to match them into the larger DNA or genome sequence. And so the sequence assembly has been around, but never really been ported to perform well on the GPUs, and fast assemblies that can consume high volumes of data is really the game here. And once you assemble the sequences, now being able to say, well, what would this sequence amend in terms of protein? So then you look at protein clustering. And so really a fantastic problem. And again, being able to have high quality assembly on 50 terabytes of environmental data. The methods are not robust for GPUs. They consume a lot of time and memory, and there's a lot of sort of fundamental algorithm development. We call motifs a common pattern of communication and computation. This sequencing algorithm has a number of motifs, hash tables in particular, but sorting dense sparse matrices has a whole kind of kitchen sink, so to speak, of computational motifs. So really, really challenging problem. Kathy and her team have done an amazing job here in developing a new code for sequencing called MetaHitmer, which is likely going to be a production sequencer at JGI, showing that with new methods for communication using a unified parallel programming language known as UPC++, showing great speed ups of 6 on 1 GPU and 30 on 6 GPUs. So this is going to be a real game changer for fast sequencing of high volumes of data. Another example, she and her team have rewritten a 40-year-old algorithm known as Smith-Waterman for matching sequences onto GPUs into an algorithm they're calling Adept. And you can see the green bars exhibit this faster, higher is faster, and tremendous speed ups. There's a nice article on this redesign. Another one in our portfolio led by Amadeo Perazzo at SLAC points to the LCLS facility. This is a light source facility, and we carefully chose this as an exemplar for how exascale computing could enhance and accelerate the understanding and processing of data on light sources like the LCLS. We chose this one because it's a really hard one. Basically, they're in the process of an upgrade where they're going to increase throughput by 1,000 in the next few years by 2025. So detector data rates at this facility are going to advance exponentially. And basically, ultra-fast X-ray pulses are used like flashes from a high-speed strobe light, producing stop-action movies of atoms, either in crystalline state or single atom state. So basically, you have these diffraction or single particle images that you're trying to reconstruct on the fly in simulation. So you can drive the experiment, tell what data can be thrown away, what data can be immediately processed, what data needs to be shipped back, say, to NERSC for more detailed processing. So there's a tremendous data challenge. Again, these pulses are used to generate lots of data, 3 orders of magnitude throughput. There are 2 kind of main codes being used here. One for femtosecond crystallography, and that's where the electrons, or 3 electrons, or then the photons in this case, are blasting through a crystalline structure, leaving a diffraction image, and then that's reconstruction. And then there's a single particle image on samples that aren't crystal in nature. And so that's even more difficult. And then the whole workflow to wrap the thing up. So again, I mentioned the computational tasks here on the left. There are real challenges here. Really trying to understand how to do the crystallography simulations well, but then moving to what we call MTIP. That's an algorithm really designed at Lawrence Berkeley by Jamie Sethian and others. Non-uniform GPU FFTs, which is very kind of non-traditional relative to a lot of our applications. X-ray tracing at the pixel level resolution. There you see the data rates, which are going to go really from tens of gigabytes per second to order terabyte per second, which is very, very daunting. So here you really want to do a lot of local processing and do as well as you can in understanding the data. So the team has devised new GPU kernels for the non-Bragg inverse problem. This really applies to the crystallography problem, but probably more impressive and more potentially game-changing is devising a fast non-uniform FFT formulation for MTIP. And this is a real stretch problem. It's going to allow the single particle imaging reconstruction to scale to many, many nodes so we can process lots of massive data sets. And again, this is in my mind, a way cool facility where a given sample will be blasted so to speak, hundreds or thousands of times. So the sample is destroyed upon when the beam hits it. So you drop another sample through the beam that's kind of like it. So it's a real challenging problem. You have multiple samples that are ideally alike but aren't. You have kind of noise in the background. The samples are moving and rotating. So it's a challenging problem to really understand what does a 3D reconstruction look like in a reliable way. So I also want to say something about workflow. So workflow, think of a workflow as I crank up a big simulation, say on Frontier, and then I do the data analysis. So step one, step two, very sequential. Well, at the exascale level, we want to do all these things, simultaneously. And there's an upstream version, ingesting a lot of data for machine learning. And so workflows are much more complicated than a single PI executing one simulation and then executing another one later for analysis. So what we're calling workflows is really a much broader definition that really would engage, say, another experimental facility at the same time. So we've stood up a new project known as ExaWorks. Just want to point out that we're really thinking long and hard about, can we build the building blocks for maybe a workflow that we don't anticipate in an agnostic way. And we bring these building blocks together for data ingestion, online data analytics, online data compression, analysis, visualization, with local simulations, say just on Frontier, but also maybe talking to an experimental facility miles or hundreds of miles away. And so we're excited about this development. We think it positions computing to move into the future of modern heterogeneous, very different workflows with different facilities being ingested at the same time. So they're engaging the workflow community. In fact, a year ago, what's called the Gordon Bell Award, 3 of the 4 finalists actually were using these components and these technologies. So we're quite confident that we're going to leave behind a software stack that supports these more advanced workflows. So encourage the audience to go take a look at this effort. It's really, I think, scratching the surface of where we need to go. I want to conclude a little bit with what we call co-design. Now, ECP is really doing co-design all across the board, from apps down to the software stack, down to the metal, and on up. But these motifs in particular are really been focusing on, and we think these we're leading to the creation of a new middleware layer for our applications. And again, a common pattern of communication or computation might include structured mesh for unstructured meshes, particles, finite element discretization, graph algorithms, and machine learning. So we're focusing on the kind of these 6 key co-design centers. And we want to point out, I think we're leaving behind some fantastic components that you can build whole applications on, and really hiding the challenges of the different GPUs and the complexities of these heterogeneity nodes to the co-design components themselves. So the AIM-RX is one, adaptive mesh refinement for structured mesh. It comes out of Lawrence Berkeley, John Bell. It's now supporting 6 applications just in ECP, and I think we're going to see it support more and more. There's a back end in terms of getting onto the metal, but it's a really nice abstraction for application developers. Another related one is for unstructured meshes, finite element discretizations known as SEED. This comes out of Lawrence Livermore, Zanio Colab. Same sort of thing here, except now we're designing for finite element PDE-based discretizations on unstructured meshes. A number of ECP applications are living on top of this component. And again, we think that these new middleware layers are going to be here for decades to come. A final one's for particles, moving discrete particles around the computational domain, mapping the particles to mesh to particles is ubiquitous across fluids, materials, plasmas. So if you're going to have a co-design center named COPA, you sure need a library named Cabana if you're a Barry Manilow fan. So this library and this whole motif, I encourage folks to look into, supporting a number of applications in ECP. And again, I'm optimistic will be used and useful much more broadly. Another one I really need to point out is CODAR. This is led by Ian Foster at Argonne National Lab, the Center for Online Data Analytics and Reduction. The point being, if you execute an exascale class simulation or even one on your laptop, you might be generating more data than you can store or afford to store at all or for very long. So you want to really process the data real time. So think about, I might have the simulation running on a few GPU nodes and real-time analytics on a few other GPU nodes. And it could be passive, meaning I'm just analyzing the data for analysis by a human later, or that and the analytics could feed back on the simulation and change the models or the algorithms real time. So a lot of really interesting aspects to this particular co-design center. And Ian and his team are really focusing on reducing the data to the parts we really care about with let's say the XFL effort, the online X-ray laser imaging efforts using, in this case, lossy compression. Online analysis, being able to analyze what does this structure look like real time in the case of molecular dynamics. Online coupling, I might have two very different distinct physics codes running on one machine, not really knowing each other's there, but we're talking back and forth with boundary conditions, initial conditions, and essentially we're coupling the codes together even though they're independent to have their own data and their own place to live on the machine. That's becoming much more ubiquitous and much more usable. So we can develop the stitching together to bring in to couple these applications. So that's being done here. And then aggregating the data, basically lots of data coming in, bringing the data together, trying to understand analytics in the data, a perfect one for machine learning and being able to deduce trained models from the larger simulation. So again, I mentioned the lossy compression. That's been a game changer for the X-ray imaging. Lossy compressor for multi-grid adaptive reduction of data. That's also very useful for coupling codes. So overall, data compression, whether it's lossy or lossless, and being able to share the data in a sort of standard format is critical for this particular effort. And we think for a lot of efforts moving forward, like cosmology, quantum chemistry, molecular dynamics, we're very excited about this effort as well. And finally, we have a co-design center, not surprisingly, focused on machine learning. In this case, really looking at how can machine learning not replace a traditional mod sim application that's, say, PDE based, but really augment and accelerate the workflow. Surrogates are very, very important. Reduced model surrogates allow us to do more productive sensitivity analysis, uncertainty quantification, being able to use, let's say, a 10 or 12 parameter model as opposed to a 1,000,000 parameter model in the raw simulation. A trained network can really get us there. Control, being able to have efficient exploration of problem spaces. In this case, reinforcement learning is very, very important. And, think of potentially controlling the accelerator, making sure the beam is on point or is focused, real-time controlling of the experiment. Very, very interesting and quite, I think possibilities are endless. Design really is optimization problems with simulations steered by machine learning. In other words, what sets of simulations do I want to do next, given what I've just learned? So if you think about firing off hundreds or thousands of molecular dynamics simulations, and I'm doing replica dynamics, and I want to understand which replicas I need to focus in on and which ones I can throw away. A lot of this sort of human intensive stuff, we can train a network to do it for us. And then last but certainly not least is inverse problems. In other words, I might look at a neutron scattering image, say of a perovskite, and if I'm trained to look at this image, I can say, well, I know what that crystalline structure looks like. I can tell you, or maybe it's one I've not seen. We better do a closer look. So think of more real-time control and real-time feedback to the experimentalist who has, just reserved precious beam time and making better use of that precious beam time. I'll conclude now in a little bit about our software stack. So what is it? It's known as E4S, Extreme Scale Scientific Software Stack. We're releasing it early and often every quarter. Consists now of 71 different products that ECP is not all developing in ourselves, but all these products we brought together. Some are new due to the project. Most we're enhancing and evolving. But the beauty is you can grab all this in a half dozen software development kits, SDKs, or grab individual pieces. They've been pre-built for you, pure bare metal, also containerized. We're really not just demonstrating way cool stuff. We're really packaging and deploying what we're doing with CI/CD, continuous integration, continuous deployment. So I encourage you to go to e4s.io. Samir Shinde, University of Oregon, is the master overall this effort, really doing a fantastic job with quarterly releases. The SPAC build packaging tool has been indispensable. Todd Gamma, Lawrence Liver has really developed an unbelievable piece of technology. All of our products, software products and applications are being built with SPAC. It's been indispensable. So we're real excited about this effort. We're deploying on the DOE facilities. we're interested in deploying at other places. We've been talking to other agencies and even some companies to help them deploy. We're deploying on the cloud, so we're really very serious about making sure the products at the end of project are deployed and continue to evolve in terms of support and maintenance. This is an eye chart. I'm just going to leave it behind. So if our applications are developed and successful in delivering on their challenge problems, the kinds of solutions are going to be generating, we think can really change the game for not just DOE, but in many cases for human quality of life. So each one of these bullets has a line of sight to a particular application we're focusing on, and we're really quite confident that the leave behind are going to be tremendous tools for science and engineering. So I'll leave this behind, but I'll give a reference to a paper where there's more detail given. And again, final takeaways, we're not just demonstrating on the largest systems in the world that maybe a few selected people can get access to. We're really demonstrating that the technologies we're developing can be game changers on your laptop, on your desktop, on engineering clusters, on up to the largest systems in the world. Deploying a stack that is used and useful at all these levels of hierarchy. Accelerated node computing, think GPUs is here to stay. And I think we're developing the abstractions that allow, that essentially lower the barrier to entry, de-risk the getting on, the ability to get on these fantastic technologies. And frankly, accelerators today will continue to evolve. So today and in the near future, GPUs, maybe better ASICs or FPGAs later. And in fact, we view quantum as just another accelerator. And so I think we're positioning our applications in our software stack to be able to exploit accelerators as they evolve moving forward. Again, our E4S is available for testing. So encourage the folks here to take a look. I'll conclude by saying there's my contact information. If you go to our website, there's a number of folks, order 30 of, I think, the best and brightest in the DOE complex to contact in various aspects of ECP, and some decent overview articles to take a look at. So that said, I will close and be happy to entertain any questions for the audience here. And again, thanks, Dan, for allowing me this opportunity. I will stop sharing.
Great. All right, thanks, Doug. Boy, that is some complex work that you're doing, and the different realms where this capacity in computing can be brought to bear as a resource is powerful. I could see where the inspiration would come every day if you think going to be working on these kind of problems facing humanity. And then, as you mentioned at the beginning, the network of different computer scientists and related resources that are part of this broader SURF network. Now that you're each aware of each other, I hope there'll be additional conversations that happen after this session.
I do too, and I'll just point out that this reflects, we have, I think, the best and the brightest involved, and we've been doing this for 5 years, and we really see the fruits of our labor. And it's a exciting time with the exascale systems being delivered. We're really excited to show in the next couple of years what we can do, what anyone can do with these technologies.
Great. Well, thanks. We have another session coming up in just another 5 minutes here.
Okay.
We will have this video, though, and make this available to our network. And I'll look to make some more connections as people reach me with questions on, I want to hear more about what Doug was saying, or just make sure they have your email address. But thanks for your time this afternoon, Doug. Very interesting.
Thank you. And I look forward to further conversations, Dan. Appreciate the opportunity to share what we're doing.
All right. You're welcome. Thanks, everybody. We'll see you in the next session in a few minutes.